Suppose you have a manifold sampled kind of like that, and what we'd like to do is project it into something like that. Okay. Now suppose that we already know the distances between every point and its k nearest neighbors. And there's overlap here because this neighbor is neighbors with that one, right? And this one is neighbors with that one, and so forth. They've all got their k nearest neighbors. Now, suppose we start doing multi-dimensional scaling and we just constrain them to be the right distances apart. Is that going to work? In fact, it does work, but here's sort of the problem. If you started in high dimensional space, do you see that basically they're already the right distance apart? So they'll just stay there, right? And in fact, that's the problem whether or not we compute the geodesicus distances. It also does nothing if you stay in the same dimensionality of space. If, however, we put all these points in one-dimensional space and maybe initialize them randomly, then start doing multi-dimensional scaling to recover the points, here's what seems to happen is you get folded over manifolds. So let me draw it like this. So imagine you're ironing a shirt, but you don't straighten out the shirt first. You kind of leave it folded over and you just start ironing, and you hold up the shirt. What's happened? Badness, right? Because the shirt just got pressed into a zigzaggy fold, and that happens with this too, right? Because there's nothing pushing it apart. Whereas if you have the geodesic distances between this one and that one are supposed to be really far apart, that kind of pushes the thing to unfold itself so you don't end up with creases and folds in the resulting manifold.
So you could just stretch everything first.
Yeah. So in 2006, 5, I guess it's 2005-ish, 2004, I invented a manifold learning algorithm, and this is how it worked. I found the k nearest neighbors. I measured the distance between every point. That's kind of the first thing you do in just about every nonlinear dimensionality reduction algorithm. Then what I did is I started scaling out the dimensionality. So suppose you're in three-dimensional space, and I wanted to go into two-dimensional space. You've all seen Star Wars, right? Turn off all the garbage compactors on the detention floor. I started just squeezing the walls in. So I picked all the dimensions I wanted to get rid of, and I scaled out the variance in that dimensionality, so the data was just getting squished. And I left the variance in the number of dimensions that you wanted to keep. So here, I'll even animate this for you. And I'll stop right there, because now it falls apart. As I scaled out the variance, I kept restoring the local relationships between the data points, and that basically worked as a manifold learning algorithm, except it had that iron press problem. Every once in a while, the manifold would be folded over on itself, and it would get smashed, and that ended up being very bad. So the algorithm was published in a top conference, which made me feel good, but then researchers started discovering, hey, this actually doesn't work very well, and that's why it doesn't work very well, is if you only look locally, you're only going to preserve locally, and you kind of need the global distances between them so you don't get folded over manifolds. So one problem is which ones should be spread out and which ones shouldn't.
Well, so
I guess you just have them be really far spread out.
Yeah, that's what I mean.
And then they're only going to pull inward if they should be pulled inward.
Yeah.
Actually, that's almost the same solution that I was going to propose. The thing is that only does it one time. So you're pushing them apart once and hoping that's enough. But what if later on some other part ends up being pulled in that needs to be pushed back out? So I'm going to propose, what if we constantly scale the points bigger and then recover local relationships, and then scale them bigger and recover local relationships, and iterate like that. Okay, turns out that works beautifully. So take our data, scale it up, and then recover local relationships. You see how that kind of forces them to get closer together. Interestingly, that also straightens them out, kind of implicitly. So this is an algorithm called maximum variance unfolding. It used to have a different name. It was called semi-definite something or other, because they used semi-definite programming approach to do their optimization step. They later figured out that was a bad name and changed it to maximum variance unfolding. The idea is, if you keep scaling up the points, in other words, you're maximizing the variance in the points, you're making them far apart from each other, but then you recover local relationships, that straightens everything out. And if you combine it with the idea of scaling away the dimensionality, I think that makes an even more elegant algorithm, because then you're not doing it all in the super high dimensional space. Okay. Unfortunately, because that algorithm, which ended up being called manifold sculpting, by the way, because that algorithm is known to have the folding over problem, it kind of got rejected by the scientific community. And so the value of scaling out the dimensions, I think, has been lost to science now. If somebody wants to publish a paper and say, hey, it turns out there was something useful in that paper long ago, there's an easy publication for somebody to poach. I think there's some value there. But for this class, we're going to get rid of that one, and we're just going to do maximum variance unfolding. So here's how this algorithm differs from isomap. One, we don't have to compute the geodesic distances between all points, because we're just going to scale them up and let that take care of it. Then we're only going to restore relationships in local neighborhoods, because we don't even know the distances to faraway neighborhoods. Do you see how that's kind of better in some ways? Okay. Here's a bad thing about maximum variance unfolding. It operates in the original high dimensional space. So here we are in two-dimensional space. Well, we can scale things up in two-dimensional space and then recover the relationships and repeat. And eventually we get the points happen to be all nicely arranged in a nice straight line, and they're all preserving the local distances between them. But the problem is we haven't lost any dimensionality. So then what do we do? Well, we happen to have this nifty little algorithm called principal component analysis. Remember, we did the very first one. And so if you do PCA on a linear manifold, you see how it's already linear, then boom, it does a really great job. You lose almost nothing because it's linear, and now you can reduce dimensionality with no loss. So maximum variance unfolding requires the extra step of PCA at the end, but skips the obnoxious step of having to apply the Floyd-Warshall algorithm to find the geodesic distances between all neighbors. And that's kind of a good thing, because a certain amount of noise is injected by the geodesic distance concept, because hopping from neighborhood to neighborhood isn't actually a very accurate way of measuring distance, right? Whereas this algorithm only relies on distances you actually do know and recovers them. So I claim this is a better algorithm, and I think most people agree with that. But isomap was first, and this one is best, and so I'm having you implement both of them in order to compare two algorithms, and hopefully you'll find this one's actually better. Okay.
Why don't you do PCA first, and then
What if you do PCA first?
so squash the dimensions you want to be in, and then do maximum variance unfolding with.
So let's take this data. Suppose you PCA that. What's going to happen? You'll get folded over things, right?
Then would stretch it first.
Okay. So you'll have to measure the nearest neighbors in high dimensional space. Mm-hmm. Then suppose we do PCA. Will that work?
Well,
I feel you've got the local optimum problem here. So let's do a folded over shirt like that. So now we scale it up, but then when we recover local relationships, I fear it might just undo the scaling rather than slide a point around that bend, because there's not a lot of wiggle room in low dimensional space. Whereas in high dimensional space, you have loads of wiggle room.
What if we just scale in
I don't know.
one?
It might work, but I'm not sure it will work. I'm actually going to just stop here and declare success, because what you're doing is nonlinear dimensionality reduction research. So awesome. Yay, everybody sit around and imagine yourself unfolding sheets and figure out the best way to do it. The answer is going to come down to go code it up, try it out, let us know. And that would be fantastic if you invent a new nonlinear dimensionality reduction algorithm. Although if you can beat this one, that's going to be hard and impressive. And if you pull it off, sweet. Now you can say, hey, I beat that one, and publish a new paper and claim to be the new king of nonlinear dimensionality reduction. Okay, let's look at, so if we look at why I'm having you do all these darn algorithms in this assignment, why are we doing PCA? Because you need it for the last step of maximum variance unfolding. Why are we doing multidimensional scaling? Because both isomap and maximum variance unfolding depend on it. Why are we doing isomap and maximum variance unfolding? Because that's what the assignment's about, is, hey, two algorithms, let's compare them. And then hopefully by comparing two algorithms rather than just doing one, you'll get deeper insights and understanding of how it all works. I could just have you omit isomap, but if you've already got multidimensional scaling, then the only thing that's missing is Floyd-Warshall algorithm, which is just a couple of for loops. And so I don't think it's actually much extra work for you. So there you go, that's the assignment. Here's what we're going to do is take this Swiss roll manifold and unfold it. And usually they use a Swiss roll manifold that doesn't have a star cut out of it. I cut out a star just because that gives us the opportunity to look at how well preserved it is in the end. By cut out a star, what I mean is I picked random points and sampled on the surface of this manifold, but if they fell within the region of a star, then I threw them out and did rejection sampling and sampled again. So yes, it's not a very pure star, but it's a sampled star. So you can see that because this manifold is curled in on itself, there's a lot of potential to have that folded over ironing board problem, right? But can you imagine yourself now unfolding this sheet by scaling up the points and then recovering the local relationships and scaling it up and recovering the local relationships? You can kind of picture that unfolding over time, right? And that's what happens. If you want to make a visualization, you can turn it into a movie, and it's all fun to watch as it unfolds itself.